Hello, and welcome to episode 6 of our nuclear physics series for grade 12 physics. This episode will look at fission, which is a type of nuclear reaction we have not yet looked at, but is quite possibly the most famous nuclear reaction that happens caused by humans in the world. So, fission is a nuclear reaction which is characterized by taking a heavy nucleus, a large nucleus, and breaking it into smaller chunks, which releases a lot of energy. So let's take a look at an example here. This is an example of a fission reaction. So in this case, we have uranium-235, which is hit by a neutron, and that neutron is absorbed and it becomes uranium-236. Now, this immediately undergoes fission into several different chunks. So the two major chunks, what are called daughter nuclei, are strontium-90 and xenon-144 in this case, plus an additional 2 free neutrons. So to go through this, what I have is I have my starting, this is called my parent nucleus, plus a neutron. They hit, the neutron is absorbed, and then it undergoes fission to become the daughter nuclei. Both strontium and xenon in this case are the daughter nuclei. In addition to that, we also have plus more free neutrons. Now, this pattern, this step here where the neutron is absorbed is an intermediate step and is not often drawn, but this is what's happening. So this intermediate step here is not always shown in this reactions, but it is happening behind the scenes, if you will. So in this case, we've got a uranium-235 nucleus that encounters a neutron and then splits. To draw this out a little bit, what I've got going here is I've got a large uranium nucleus. I've got a small neutron which comes in and hits that nucleus. That nucleus then breaks apart into two smaller chunks of a strontium. So that breaks apart into strontium and xenon, and an additional 2 fast neutrons here. So this here is the starting. It breaks into these chunks here. A couple of things to note about fission. This is an example of the fission of uranium-235. When fission happens, it does not always break into the same chunks. It breaks into things that are approximately 1/3 and approximately 2/3 of the size of the original. That's a very approximate, but our conservation laws still apply. In this case, I have 235 nucleons in the uranium plus 1 neutron. I must end up with 236 neutrons here, or nucleons total here. Notice there are 2 neutrons. Same thing, charge must also be conserved for this. Now, just like any other nuclear reaction, I can find the energy released by this by finding the mass before and finding the mass after. However, for this one, I would need to go look up the masses in my mass table. So if I go look at my isotope mass table here, I can find way down at the bottom uranium here. Practinium, here's uranium. So if I take a look for uranium-235, here's my mass. And then I could find strontium and xenon and find those masses and find the energy released. I'm not going to go through that because it's exactly the same process as we could for any of our other nuclear reactions. However, This isotope mass table you will be able to find in the class notebook if you need it. So with our fission reaction here, we can find the energy released. It breaks into separate chunks, but there's a really important part of this. When we have a fission reaction occur, we end up with extra neutrons here. These extra free neutrons are very important. These extra free neutrons can continue on and encounter other uranium atoms. So if I have these two free neutrons from this reaction here encountering other uranium atoms, I have what's called a chain reaction. The idea is one uranium fission releases neutrons that cause other uranium fissions. And because each reaction releases multiple free neutrons, which might be 2, it might be 3, it might be many more. Actually, it's generally only 2 or 3. What's going on is that each generation, you end up doubling or tripling the number of fusion reactions that happen. This happens very quickly, very, very quickly. So this process is called a nuclear chain reaction or a fission chain reaction, and is the process that is the key behind a nuclear bomb or a nuclear reactor. A nuclear reactor is a controlled fission reaction where we deliberately limit how many neutrons can cause additional fission reactions. If you can limit that to approximately 1 neutron per reaction, what happens is you have a sustaining rate where it continues at the same rate for a long time. If you do not limit these, if this is an uncontrolled chain reaction, every generation you double or triple the number of fusions that happen, and you end up with a very, very large number of reactions happening. Again, this is an exponential growth case. You end up with a very large number of reactions happening in a very short period of time, and all of that energy is released at once. This is the simple version of fission here. The idea, really straightforward. Fission is breaking apart a large element. Now, one thing to note, when we look at our binding energy, the binding energy of these atoms tells us how much energy is released. One thing that is useful to note, we look at a chart here of average binding energy per nucleon. We see that, for example, hydrogen 1, there's only 1 nucleon. But as we go with the light elements, the average binding energy increases. Iron here has the most binding energy per nucleon, iron 56. This is the peak of this curve. Uranium is down here. So fission breaks large elements into smaller chunks, so it moves us to the left on this graph. In order to release energy, you need to move up on this graph. So fission will only work when we're talking about elements that are heavier than iron. If we try and split things that are lighter than iron, it will not release energy. So fission releases energy by breaking large atoms, large nuclei into smaller chunks. I hope this makes sense. Have a great day, and thanks for watching.